Hello and welcome. Today we are going to talk about how do we separate a non-linear dataset using a linear classifier using what is known as a kernel trick. We shall understand why this is referred to as a trick and not a technique. But before moving ahead, I am Saurav Agarwal. You are watching Datahat Unfolding Mystery. If you are new to the channel, don't forget to subscribe, hit the bell icon, share with the friends and data science enthusiasts, because here we talk of learning, creating and collaborating. Last week, we shared about some of the opportunities in the domain of high performance computing, quantum computing, edge computing. If you find these useful, if you find these interesting, go check the video. I'll attach it in the I button above. And also, if you think that you face certain difficulties in understanding these concepts, make sure to put it down in the comments and I'll definitely help you out. Trust me, it is not difficult. It is just with the right process that you will achieve what you want. So now let us get back to what is kernel trick. But before moving ahead, we need to understand what we are going to discuss in this video. We shall understand the context behind the kernel trick. We shall see with an example. We shall look at what kernel trick actually means, why should we use kernel trick and not anything else, choosing the right kernel, and finally we shall summarize what we have learned so far. So consider an example of classifying a non-linearly separable data, which you can very well easily understand using a linear classifier such as KNN, logistic regression, etc. Okay, now you understand that we have a linear classifier and we have a non-linear data set. One of the approaches, what would be one of the approaches, is to augment our feature set in order to convert them from d-dimensional to d-dimensional or a higher dimensional such that they become linearly separable. Now this augmentation technique, let us call this lifting for a while. It may be referred to as something else, we are not aware of it. Let us call this as lifting. Okay. Now the example, let our data be referred to as vectors x1 y1 x2 y2 xn yn. So there are n data points and this xn belongs to d dimensions, so each of these are d dimensional vectors. Now say for d equal to 2, as for example here, so we'll have x is equals to x1 x2 and the transformation function is defined as x1 square x2 square square root of 2 x1 x2. Just understand what I'm trying to say. Just don't try to make a logical conclusion of it yet. Just understand the example that we are laying forward. Okay, so this is a transformation function which will apply to our vector, okay, in order to get this, and the dimensionality of this transformed vector is now 3 because we have 3 parts to it. Earlier d was 2, now d dash is 3. Now in order to find a hyperplane in this new feature space, we transform our original vector x to this new feature vector phi x, and this phi x is such that d dash is greater than d. Okay, now in this new feature space, in this higher dimensional feature space, we can apply the linear classifier and classify our data set. Okay, now everything looks good. Now what if we could avoid computing phi x entirely while still doing linear classification in this lifted space using a trick? Now why we will call this as a trick? Because it is rather a hack. Okay, it is a hack. It is not a complete method in itself. Okay, now coming to the kernel trick. You must have heard of SVM. If not, understand that SVM is a linear machine learning classifier. We shall discuss about SVM in detail in a separate video, but just understand it is a machine learning classifier. And the loss function of this SVM support vector machine is given as this. Okay, just don't try to understand each of the different variables given here. It might appear dangerous at first, but it is not. It just uses a Lagrange multiplier and the different mathematical concepts, and it is a dual form of the original loss function, which is the hinge loss. Okay, now just take it for my word that this is the loss function for SVM. Now you see this loss function contains a dot product between xn and xm. So dot product between the two inputs basically the data points. So since it contains a dot product, it is a linear classifier. Okay, understand this. Now our point here is SVM requires a dot product, therefore they are linear classifiers. We could very well use the lifting trick here and apply our transformation. Now we could very well apply transformation in this space using our lifting technique, which we refer to as lifting, and convert it into this space. Now what happens is, the number of operations that we require for this process is, first we have to make the feature transformation. So we would require d dash operations, because d dash would be the new dimensionality, so d dash operations. So understand. Now if we have n data points, so it would be n d dash. Then we perform an inner product on those d dash. Okay, this is the inner product. We have 3 cross 3, so 3 operations, and then sum them up. So just for this example, if you consider, we would have 2 into 3, because we have 2 vectors. So 2 into 3, 6 operations, plus 3 summation operations, okay, and 3 inner product operations. We had 6 transformation operations, 3 inner product operations, and 1 summation operation, which equals 10 operations for just this one particular one, for this specific data points, 2 data points. Okay, so we'll have 10 operations. Now the problem with this approach is scalability. What if you want to scale it up? Okay, there would be very challenging in terms of the computational resource that you require. Now what we take an alternative approach. Now what is an alternative approach? So the alternative approach is, instead of converting, or instead of using 5x transformation on our feature space, what if we first take the dot product, sum them up, and then square it up? Basically, square is just a function here. The function could vary depending on the kernel that we use. Now you understand what is the kernel. The kernel is basically the operation which would be applied to your dot product or the inner product, such that it transforms your feature space without actually transforming your data points. Okay, you see from this example, when we square this up, you are getting the exact same result as you got using this transformation first. So you first transformed them, then you took the dot product. Whatever result you got, you're getting the same result when you first take the dot product, do the summation, and then square it up. Now the number of operations that we require in this process is, we require d operations for the dot product. Okay, d dimensional d operations, because we don't have any transformation, so no 0 on that. 1 summation, and then 1 square of scalar, so total 4 operations. So now we see here that it requires only 4 operations as compared to 10 operations in case of the lifting trick. That is what makes kernel tricks so powerful. That is why they are extensively used in SVM for classifying non-linearly separable dataset using linear classifier, that is SVM. Now that you are convinced with the power of kernel trick and why that is called as a trick, I would again request you, if you haven't subscribed to the channel yet, make sure to subscribe, hit the bell icon, because we are going to bring a lot more surprises in the coming days, in the coming weeks, in the coming months, and the whole year. So now next we'll move on to how do we decide which kernel to choose. Okay, very well, I convinced you that you should use a kernel trick, but again, kernel is also a method. Whether you should square it up, whether you should cube it, whether you should take the square root, how you should decide it. So now the burden of this has already been taken care of by data scientists over the years, and they have shortlisted certain kernels which perform incredibly well across situations, across different types of data sets. And here we have a list of some of them. So some of the primarily major kernels that are used are the Gaussian radial-basis function. This is used whenever you have no idea of what the data set looks like, what the data set is about, so you apply a Gaussian radial-basis function. However, this is also a complex form, so we first approach it with the simplest of form, that is a linear kernel, then probably try a polynomial kernel or a sigmoid based kernel, and then go for the Gaussian kernel. This comes under the process of cross validation. You evaluate your model by using different kernels and see which works best, but you don't have to go in an infinite space to search for the appropriate kernel. You just have to select among these 4 or 5 of them. Now you see from here that Gaussian radial-basis kernel is a kind of a Gaussian function. Sigmoid kernel is basically similar to the activation function, sigmoid, tan h, relu, those things. Polynomial kernel is just the square, cube, the different d dimensions, as you can see from the image as well. Linear kernel is nothing, just a linear operation on the original dot product. Some other kernels also include Gaussian kernel, Basel kernel, ANOVA kernel. If you want to learn about these, I'll have attached the link here. I'll also attach it in the description. You can go read them out. If you face any difficulties, make sure to put it in the comments. I'll help you out. Now, again, as we do in all our videos, here is a small thought for our viewers, that when we dedicate ourselves to a cause greater than ourselves, we experience growth, we experience real growth. And you have to trust me on that, because you are going to experience real growth when you dedicate yourself to a cause which is greater than yourself. That cause could be anything, that could depend on your dreams, your aspirations, but remember to have a cause which is greater than yourself. It will take time, but we'll soon have it. Now, coming to the summary of it, we understood what kernel trick and why kernel trick is referred to as a trick and not as a method, what is the primary advantage of kernel trick, and how does it classify a non-linearly separable data set to a linearly separable data set. When we learn about SVM, we'll talk more about it, how to actually apply it in use cases, and also how scikit-learn implementation may allows you the same. But here, make sure, if you like the video, make sure to subscribe, hit the bell icon, share with the friends and data science enthusiasts. See you in the next video. Have a nice day. Bye bye. Jai Hind.